Struggling to draw an accurate tangent to find out the gradients of a curved graph? Well, you should definitely learn about derivatives. First, we have to grasp the concept of limits. Limits are similar to solving a function by substituting an x value, except that the x value never gets equal, but just gets closer and closer and is put to its limit up to the thousandth decimal point. For example, in this function, as the x value gets closer but not equal to 2, the y value gets closer to 3. We can also modify equations if they don't make sense. For example, 0 over 0. We get the gradient of a straight line by dividing the rise over the run, which is the change in the y value over the change in the x value. On curved graphs, we can similarly get the gradient on a certain point, just by adding a limit sign in front. There are 2 points on the graph y equals to fx, a, fa, and b, fb. The average rate of change will be fb minus fa over b minus a, rise over run. But we want to express this with just a so that the equation will be way more simple. Hence, we say that delta x is the change in the x value, b minus a. Since delta x is equal to b minus a, b is then equal to delta x plus a, and this becomes the simplified equation. Since delta x is a constant, it can be changed to any other value or unknown quantity. Let's say h. Remember when I said we need to send this equation to its limit? This is because we need to get the rise and run to get the gradient. But since the graph is curved, we make delta x the smallest it can be by sending it to its limit, so that when the graph is expanded, the 2 points a, fa and b, fb lie on the graph and still make a straight line. So b, fb is sort of an imaginary point that is so close to a, fa just to guide us finding the gradient. Now we write the limit sign in front, sending delta x or h to 0. Here we see that a plus delta x equals to any constant, so it can be b, z, or even x. As delta x gets closer to 0 and almost disappears, a becomes closer but not equal to x. Ta-da! These 3 equations, also known as f prime a, are the derivatives to find out the gradient of a point in literally any function. Cool, isn't it?